Question 15. You've got a layer of oil which is floating on water in a glass container. So you got oil floating on water, and there is your glass container around the outside. And around the outside there, you've got air. And the diagram says it's not to scale, so you're not getting a protractor out trying to measure any of these angles, because the size of the angles is not the same, as the scale is not correct. So the incoming angle, the light comes in, hits the glass, that ray is perfectly perpendicular to the surface, it goes straight through, perpendicular to the surface, goes straight through without bending, goes through into the oil and hits the oil water boundary and refracts. And there's theta, incoming angle, incident angle, 44 degrees. So here are the respective refractive indexes. So the oil has a refractive index of 1.47, the water has a refractive index of 1.33, and the glass also has a refractive index of 1.47. So both the glass and the oil have the same refractive indexes. So show that the angle of refraction, theta, is approximately 50 degrees. So we are going to use Snell's law here because we are given refractive indexes and angles. So Snell's law is written here. I like to write down the medium in which the ray is at so I don't get the numbers mixed up. So all I've done is replace the ones and the twos with the name of the mediums, oil and water. Okay, because that's where the light is when it is incoming, hitting the oil water boundary and entering into the oil. And what we see is we put in the numbers, the refractive indexes and the angles respectively, rearrange, and we get an angle of 50.15 degrees, approximately 50 degrees there. Now the way you set up that question is quite nice and straightforward. Start off Snell's law, plug in the numbers and get to your answer. Part B of this question asks you to draw so the oil and the glass have the same refractive index. On the diagram above, draw a path of the light ray after it strikes the boundary between the water and the glass and enters the glass. Show the value of the angle of refraction in the glass. So it's between the water and the glass and it entering the glass. So let's have a look. So this here is part B. So it leaves the water here, enters the glass. And because you're going from water into glass and you're going from water, low refractive index to high refractive index, that shows that light slows down a little bit more in glass compared to water. The optical density is greater in glass compared to water as well. So we know that light slows down and bends towards the normal, and there is a line showing that it's bent towards the normal. And this angle here, the way that the light bends, no calculation is required, and it's 44 degrees because we know that the refractive index of glass is the same as oil. So if the light entered water from oil with an incident angle of 44 degrees, and this layer are parallel, then if it's going to a medium which has the same refractive index as the oil, then the angle of refraction will go back to 44 degrees. Now, if this was oil, this layer was oil, then that would have definitely been 44 degrees as well. Because they both have the same refractive index, that's the same thing's going to happen. The incident light will bend back towards the normal at that same angle. The next question is explain why the total internal reflection will not occur when the ray travels from water to glass. So why does total internal reflection not occur when the ray goes from water into glass? Okay, so going from water into glass, why doesn't it hit and bounce off? Now, it will never totally internally reflect, because one of the conditions for total internal reflection is that the refractive index of where the light is going to has to be greater than where it's ending up. So here, the refractive index of water is less than glass. Therefore, no internal reflection is ever going to happen. Okay, so total internal refraction only happens when you go from a high refractive index to low refractive index. So that's the condition. That's only when total internal reflection could ever happen. Okay, so here we've got the opposite, where the refractive index of water is less than the refractive index of glass. Whereas if light was going from glass into water, there is a possibility of light totally internally reflecting back the other way, because refractive index of glass is greater than the refractive index of water. Another way of answering this question is to say that the optical optical density of water is less than the optical density of glass. Therefore, no total internal reflection will occur. And remember the word optical, because that's key. Calculate the critical angle for the boundary between glass and air. Okay, so the critical angle, sine of the critical angle, is equal to the refractive index of where the light ray is trying to get to, divided by refractive index of where the light ray initially is at. So that is going from glass to air, trying to get to air, and is in light rays in glass. So if we rearrange, we know that the refractive index of air is 1. That's where it's trying to get to. And it's the light ray initially is in glass, which has a refractive index of 1.47. So the critical angle is 42.9 degrees. So the critical angle between the glass air boundary is 42.9 degrees. So what does that mean? Any incident angle above 42.9 degrees, the light ray will totally internally reflect. If the angle of incidence is less than 42.9 degrees, then you'll get refraction. Light will pass through and it will refract. So on the diagram above, complete the path of the ray after it strikes the boundary between the glass and air. So let's have a look. We've already drawn this. When light hits the glass air boundary here, that angle there is 44 degrees. That angle there, incident angle there, therefore is also 44 degrees. There you go. There's a Z there. Okay, using the normals as a guide. So this angle and this angle is 44 degrees. So the incident angle on the glass air boundary is 44 degrees. We know that is greater than the critical angle of 42.9 degrees. Therefore, light will totally internally reflect, hit that boundary, bounce off, hit that boundary, and it's going to less dense region, and that angle is also 44, so it's going to bounce refract away from the normal, the same as it came in on this side, as all of these boundaries are parallel to one another, and then it's going to refract back in towards the normal, just as it did when it came in, and back straight out that way, just like that. So it's just it's quite symmetrical in the way it's drawn. So that line there and that line there are required for part E.